Hi there, my name is Colin and I'll be your guide through this module of Day 9. We're going to talk about differential equations. Please don't forget to pause this presentation at any time if you need more time to think about something. We're going to have a look at some applications of mathematics in the next couple of modules. The most important application of mathematics to real-world phenomena are differential equations. A differential equation is nothing more than an equation involving an unknown function and its derivative. We're just going to look at a family of examples of differential equations, which will allow us to study population growth. Let's have a think about the most important property that a basic model of population growth should satisfy. The assumption that a population grows at a rate proportional to itself makes sense when you think about it. Indeed, if there's more people around, there's a greater potential for the creation of more people. We can write the above assumption in mathematical notation. The rate of change of a population is its derivative with respect to time. Saying this is proportional to its size is simply saying that dp dt equals k times p for some constant k. K will be positive because we want the rate of change to be positive. Otherwise, the population will be decreasing. This is an important idea, rewriting an English sentence into mathematical notation. We should pause to take a moment and think about this model, which is definitely not perfect. In a real-world scenario, there are millions of different things which influence the growth rate of a population other than its current size. Predation, food supply, temperature are just a few, and I'm sure you can think of more. By necessity, any mathematical model which is trying to describe real-world phenomena will fall short of the infinite complexity of reality. But better and better models can become better and better approximations to the real world. We want to solve this differential equation. That is, to find a function which satisfies it. It's easy to show that any function of the form p0 times e to the kt, where p0 is the initial population size, satisfies the equation. Indeed, if we differentiate this function using the chain rule, the k comes out in front, and we see that dp dt equals k times p, which is what we want. In fact, we can make this model significantly better if we change to a slightly more sophisticated assumption, namely that a population grows proportional to the difference between itself and some fixed quantity m. This means that as a population gets closer and closer to the value m, so the difference p minus m gets smaller, the growth rate slows. This is a phenomenon which is observable in the real world, where physical limitations prohibit the infinite population growth of our previous model. By similar reasoning to before, we can write our assumption in mathematical notation as dp dt equals k times p minus m. Remember, we're saying that the rate of change is proportional to the difference between p and some fixed number m. Let's show that any function of the form p equals m plus ae to the kt for a constant a satisfies the differential equation. If we differentiate, the m goes away. Remember, it's a constant. And the chain rule brings a k down in front of the ae to the kt. But ae to the kt is p minus m, so dp dt equals k times p minus m, as required. Let's have a look at an example of this model, applied to a slightly different real-world phenomenon. Isaac Newton proposed that the temperature of a hot object can be also modeled by this very same equation, using some negative constant k, and letting m be the ambient temperature. Suppose we have a room in which the temperature is 25 degrees, and we place in this room a cup of hot coffee. Then the temperature big T of the coffee will decrease at a rate proportional to big T minus 25, the difference between the coffee's temperature and the room's temperature. K is negative here because we want the rate of change to be negative. As we saw before, the solution looks like this. The temperature at a time t is given by 25 plus ae to the kt, where a is some constant. Alright, let's have a think about some of these questions. Suppose the coffee is initially 70 degrees, and that after 10 minutes it is 40 degrees. How can we find the temperature after a further 10 minutes? That is, how hot is the coffee after being in the room for 20 minutes? Well, first we need to know the values of our constants a and k. Then we can just plug in t equals 20 to get the temperature at time 20 minutes. We know t of 0 equals 70, so plugging this into our function, we see 70 equals 25 plus a, which means a equals 45. But we also know t of 10 equals 40. Plugging this in, we get 40 is equal to 25 plus 45 e to the 10k. If we rearrange, we have 45 e to the 10k equals 15. So e to the 10k equals 1 on 3. Taking natural logarithms of both sides gives 10k equals ln 1 on 3, which simplifies to negative ln 3. So k is a tenth of negative ln 3, which is roughly minus 0.11. So we now know both constants and have an explicit equation for the temperature at time t. Big T equals 25 plus 45 e to the kt, where k equals negative 0.10986, correct to 5 decimal places. To find the temperature after 20 minutes then, we just plug in t equals 20 and see that big T is 30. The second question asked how long it takes for the coffee to cool to 27 degrees. This means we want to set big T to be 27 and solve for little t. We can rearrange by subtracting 25 from both sides, and then divide by 45. We can then cancel out the exponential on the left-hand side by taking natural logs of both sides. T is therefore 28.6. This means that it takes around 28.6 minutes for the coffee to cool to 27 degrees. Finally, we want to draw a graph of the temperature against time. Here is our function which we considered earlier on. And we have the coordinates of 3 points on our curve. And we know it approaches 25 as t goes to infinity. So, the graph will look something like this. Notice that 25 is an asymptote for the graph. That is, as time goes on, the temperature of the coffee will get closer and closer to 25 degrees. Alright, have a go at these practice questions to get a feel for differential equations and Newton's law of cooling. Press pause, and then press play when you want to continue. And here are the answers to part 3.